Official notice that the meeting is going to be recorded.
Yeah, just a heads up. So welcome everyone to Beginner Track Workshop 7. Thank you for coming. In this workshop, we're gonna be implementing linear regression from the ground up using a Google Colab. So I'm gonna start screen sharing. Can you guys see my screen? All right, so
yeah,
let's start with a brand new Google Colab notebook. I encourage you guys to follow what I'm doing. So I guess start with a new notebook. Because it'll be a lot more interactive if you guys do what I'm doing. All right. So this is the first of 2 guided workshop series in a beginner track, and we'll be doing linear regression today. All right. Is everyone on the same page? Okay, I guess we can wait for a few minutes since people are still joining. All right, for those of you guys who just joined, I would encourage you guys to start a brand new Google Colab and follow what I'm doing on screen. I guess if you guys have a Google Colab ready, then do the, I guess, a thumbs up emoji or reaction. So it's easier for me to tell. All right, let's start with some import statements. So, oh yeah, import modules. All right, we'll be using NumPy for this workshop, as well as pandas and matplotlib. Import matplotlib.pyplot as PLT. All right, I guess if you guys are caught up, then please do another reaction so it's easier for me to tell. All right, looks like we're good. If you guys have any questions during the workshop, feel free to interrupt me and ask your question, or unmute yourself and ask. So the first thing we're gonna do in this guided project is to model a line using linear regression. And wait, cell doesn't copy. Okay, let's add a Markdown Cell. So the function that we're trying to learn is okay, hopefully this works. Okay, that's kind of awkward. So we're trying to model this line, which is f of x equals pi times x plus 10. So here is the first exercise that I would like you guys to try, which is to implement f of x. All right, so this should be implemented using like one line only. So if any of you guys have the answer, then feel free to type it in chat. Okay, yeah, I can zoom in. Is this good?
Yeah, could you repeat what you want us to write the code for? Is it the...
It's just implementing this function that we're trying to learn, which is just a line. So this should return something, which is the output of this function.
So could you just do return pi times x plus 10?
Yes, that is exactly the right answer. So to get pi in Python, there's a number of ways to get pi. So one of them is just with np.pi, because we import numpy as np. So yeah. Okay, someone asked, wait, can you show how to get the LaTeX function collab? Yes, so if you have a Markdown cell, like so, so how you do LaTeX equation is you want to start with $2, and then you want to enclose what you're gonna type within the $. So for example, I can type f of x equals x. So this will show us LaTeX. You can also do like a bunch of cool stuff like yeah, there's a lot of, if you want to do fractions, for example, you can do the frac, and then this would show us a fraction. So basically, so to summarize, you just do it with a Markdown cell, and then you enclose what you're gonna type in the LaTeX with $2 on each side. Does that answer your question? All right.
What did you mean by a Markdown cell?
Oh, it's just the text, add text cell. Sorry, that was a kind of a Jupyter Notebook term, the Markdown cell thing. I guess in Google Colab it's called text. All right, so hopefully everyone is good with that. So the next exercise is so like, in order to do machine learning, we need some data. So let's generate 100 data points in the range of -5 and 5. So I'll give you guys a minute to, I guess, think about it. And if someone has the answer, feel free to post it in chat. We're storing the, I guess, the data in a variable called x. Okay, someone answer x equals np dot linspace -5, 500. So that's the right answer. So just to reiterate, the first value is the, I guess, starting point. The second value is the endpoint, and the third value would stand for the number of data points that we want. So since I defined n to be 100, I'm just gonna pass in n. And so here's an example of passing by name in Python. And this is often quite useful because like for a function like linspace, like there could be a lot of parameters and you might not always remember the exact position of each argument. So by passing in the parameter by name, you don't necessarily have to remember the exact position of the argument. All right, so let's reshape our data to, I guess, 2 dimensions. And let's print out the shape. So as we expected, it's gonna, the dimension of x is 1 by 100. So what that means is x has 1 row and 100 columns. And we're gonna also define y to be f of x. And we can also print out the shape of y, which is also 1 by 100. All right. Is everyone good at this point? Feel free to ask any questions. Let me check the chat real quick. Okay. Looks like we're good. All right, so let's initialize our weights and biases randomly. Weight and bias randomly. All right, so I guess between 0 and 1. So this would be, all right, so our weight should be, okay, maybe I should do a markdown cell first. Yeah, actually that's a good idea. So, okay. Can everyone see the hypothesis? Okay, zooming in is actually throwing me off. All right, so this is our hypothesis as a reminder. And since we only have one feature, our weight is has only 1 dimension. And so, all right. I guess I'll wait for a minute for you guys to think about like how to implement. Why does y have a shape? Oh, because like, I guess since I'm passing in y into f, and since x is 1 by 100, then y is also 1 by 100 because I'm just passing it into a linear function. And I guess, all right, does anyone want to guess how to initialize the weights and bias randomly? np.random.random. Okay, that's close. So the correct answer is np.random.rand1. And it's the same for B because these only have 1 dimensions. So we can print out W, I guess. Just, yeah, so it's a random value between 0 and 1 with only 1 dimension. All right. Looks like we're getting some questions. Is there a shorthand to get the function's parameters to pop up? So I think for Go Colab, I'm pretty sure the short documentation will pop up if you type the function. Like you can see like this documentation here. I think for a Jupyter notebook, it's probably tab or shift tab. But yeah, you can, if you type np.linspace, you'll get like a short documentation. So that's pretty cool. Another way would just to, I guess, Google it, which doesn't take that much more time. All right, so let's define y hat now, since we have initialized our weights and bias randomly. So, all right, this should be one line as well. Okay. So we want to take in our weights, our bias, and our x's. I'm gonna wait for another minute for you guys to attempt. So if you have the answer, feel free to post it in chat. All right, someone said return w times x plus b. Yes, that's correct. All right, so let's do some visualization now with matplotlib. So let's plot I guess, the f of x first, and then we'll plot what our y hat looks like. So, so it's x comma y. So this should output. Yep. So this is the line that we're trying to model with linear regression. And let's plot what our y hat looks like with the random weights. All right, so the line that we're trying to, so the y hat we have now is close to horizontal, which is as expected because we initialize our weights and biases randomly between 0 and 1. Actually, let's check. Let me check chat real quick. Okay, there's no questions, so we're good. All right, so I guess the next step would really be to just implement our loss function at this point. And let me just remind you guys what the loss function we're gonna use is gonna look like. Wait. Why is the app cell option not showing up? Oh, apparently that restarts everything. Okay. I guess run all. All right. So we're going to be using mean square error for this. And I guess the next exercise would be defining mean square error as a function. So this is going to take in y and y hat. And this should be implementable in, I guess, between 1 and 2 lines. So I'm just going to add a comment real quick. In the meantime, feel free to, I'll give you guys a minute to think about this. And then if you have the answer, then feel free to post it in chat. we have some questions. Someone asked, why don't we have to call plt.show? I guess for Colab, it doesn't really matter in my experience. Like, it's definitely like, I guess, good practice to call plt show. But I guess for Google Colab, it doesn't really matter. Okay, someone asked, can you go over your y-hat code really quickly? So yeah, so our y-hat, since we're only dealing with one feature, so our w is just, I guess, a scalar, and our bias is also a scalar. So y-hat takes in, since yeah, we're not. Yeah, I guess technically, like, since w and b are like global variables, so you don't really have to pass them into y-hat, but I guess it's just, I guess, good programming practice to do so, because like sometimes you might not want to define like global variables, but I guess in this case, like, since they're global, it's not necessary. Okay, someone answered n equals y dot shape sub 1, return 1 over n times sum. Okay. Yes, that looks correct, except I think the square has to be like within sum, if that makes sense, because you want to square it before you sum up the values instead of summing the values and then squaring it. But I guess another way you could do it is just by using np.average, which is the same as just taking the sum and then divided by n. And then we're going to use another pair of parentheses in order to make sure that we're squaring it first and then we're averaging it, if that makes sense. All right, so we're going to go through np dot real quick, because I don't think we covered it during the NumPy demo. And it's kind of important that because this is kind of important for the guided project, so I kind of want to go through this before we delve any deeper. So let's start with a matrix, I guess, with one dimension, excuse me. And let's just set b equals a. And let's double check what the shape is. So a is 1 by 3, and b is also 1 by 3, since it's basically just a. So does anyone want to take a guess what np dot a comma b is? This is just the standard matrix multiplication operator, I guess. Dot product. Yes, I guess for one-dimensional matrices, equivalent to dot product. Okay. Someone answered 14, and that's not a bad guess, except you're gonna get an error, because in order to multiply two matrices together, you have to make sure the second dimension of the matrix, of the first matrix, which is 3, is equal to the first dimension of the second matrix. So an easy way to fix this is just to transpose the second matrix. So, okay, so b dot t, the transpose of b is, I guess I have to call shape. This is 3 by 1, so we're multiplying a 1 by 3 matrix by a 3 by 1 matrix. So we're gonna get a 1 by 1 result. So another thing to note is the order does matter. So if you transpose A instead, you get a 3 by 3 matrix. But I guess the details in how matrix multiplication like doesn't really matter that much. I guess a good practice for bug fixing would just be like checking the shape of the stuff that you're multiplying and then just making sure the dimension line up, and that's usually enough for you to, I guess, debug your code. And another interesting thing you could do with matrices in NumPy is to multiply them using the standard multiplication operator. So does anyone want to guess what A times B is going to output? All right, someone answer 1, 4, 9, and that is correct, because so if we multiply two matrices that have the exact same dimension together using the asterisk operator, I guess, you're basically just multiplying each element in the matrix like element wise. So we're multiplying 1 by 1, 2 by 2, and 3 by 3. So this would give us 1, 4, and 9. So very good. All right, I guess now that we've gone through how np.dot works, we're equipped to basically, I guess, calculate a gradient for our thing. Okay, so you can actually add a cell. Okay, I didn't know that. That was kind of awkward. All right, so here are the equations for our gradients. So since we only have one weight in our this example, so I guess del L del W is just a one dimension thing for each training example. So, all right. Does anyone have any questions about the gradient before we implement it with code? Okay, Adithya said something. All right, cool. Thanks for clarifying. All right, if there's no questions, let's implement our gradients. This is slightly more involved compared to the previous exercise that we did. So I guess I'll just start working on this, and then I guess, yeah, let's define our gradients as a dictionary. So we're just initializing an empty dictionary. And I guess what we're gonna do is just storing our gradients into this dictionary with, I guess we can just call them dw for del L and del W, and dB for del L del B. And I will give you guys, I guess, 2 minutes for this because this is slightly more involved than the previous exercise that we did. And obviously want to return grats, and also those have a typo. All right. Let me add a comment. Okay, so I guess someone asked like, why should we use the dictionary instead of something like a list? So that's a great question because a list could work just as well. But I guess for readability purposes, I personally prefer using a dictionary for gradients just because, like, dw is gonna be it's gonna always stand for the partial derivative of the loss function with respect to the weight. So if you use like a list, you have to kind of just remember which index is the gradient in respect to the weight and which one is the bias. So this could potentially lead to some bug if you're not careful about it. But yes, you can just use a list, and it will work basically the same. An array be faster because of optimized operation. Okay, so how a dictionary is implemented is, for those of you who have heard of hash table, the built-in dictionary for Python is implemented with a hash table. So to access an element from the dictionary is actually linear time. So it's definitely pretty fast to access an element once you have stored it into the dictionary. Or my bad, it's constant time, not linear time. So it's O of 1. Yeah. All right, does anyone want to, I guess, take a guess at any one of these gradients? Okay. All right, so someone answered, someone answered the gradient in respect to the weight is 2 times np dot average, y hat minus y times x. That's a pretty good guess, but we have to note that we're actually doing matrix multiplication when we're multiplying y hat minus y times x, because like these are all matrices. So the y minus y has 1 by 100 matrix, and x is also a 1 by 100 matrix. So the correct answer would be 2 divided by n times np dot. Can't really type today for some reason. Y hat minus y. And then the important thing here is we have to transpose x. And I think someone also have an answer for the second one. db equals 2 times np dot average y hat minus y. Yes, so that is correct because, yeah, okay. So that is exactly the right answer, so good job. I guess you can also use np dot sum. Okay, very nice. Does anyone have any questions regarding to what we just did? I guess, yeah, if you guys can do like a reaction real quick, that would be nice. All right, it looks like most of us are good. So we're gonna move on to the actual training of our model, which is the gradient descent and all that good stuff. So we're gonna, I guess, use another Markdown cell. Oh wait, someone has a question. Why does DW not need the average part? Does NP dot dot include summation? Okay, I guess to answer this question, I guess, okay, is annotation enabled? Okay, it is, okay. So, okay, I guess let's print the shape of Y and the shape of X. So let's just double check. This should be 1 by 100. And X is also 1 by 100. So essentially how, what NP dot dot Y minus Y hat, which, or Y hat minus Y, which has the same dimension as Y, is, okay, let me get my, all right. I can't really write on screen, but, oh wait, it's in the wrong orientation. So this is Y, and this is 1 by 100, like we just inspected. So I'm just gonna add some like random values. Just bear with me for a second because I can't, like, I'm not an artist, so I can't actually. So what we're doing with X is we're transposing it, so it's 100 by 1, meaning it has 100 rows and 1 column. So essentially how NP dot dot works in this case is we're taking the dot products between these two. So we're multiplying 1 by 1 here, or the first element in Y hat minus 1 by the first element in X, and the second element in, so, okay, actually it'll be probably better if I just write it. So the first element by Y in Y minus Y hat, but I'm just saying, actually I guess I'll just, for the sake of completeness, I'll just say this is Y hat minus Y. So this is 1 times 1 plus okay, wait. Plus 2 times 2, and so on, up to 100. So we're just taking this, so by multiplying, we're basically just taking the dot product. And then, so that basically acts like this summing everything from, with the indices. You can also implement this with a for loop, but, and that would be a pretty good exercise, I guess. But I guess since NumPy already has all these built-in matrix multiplication, we could just take advantage of it. Okay, someone asked, why is matrix multiplication of Y and X transpose not the same as the sum of the Hadamard product? Okay, so the dot product is, oh god, wow, I have to draw this again. Okay, so with the dot products, we're adding up all the, like the products of all the element, like, and the products of all the entries. So we're multiplying the first elements in Y hat minus Y to the first element in X, and then we're adding that to the products of the second element in Y hat minus Y times the second element in X. Yeah, so we're dealing only with vectors. So if we take the Hadamard product, we'll end up with another matrix that's 1 by 100, consisting of the product, the element Y's products between Y hat minus Y and X. And you wouldn't have to transpose X because you want these two to have the exact same dimension in order for the Hadamard product to work. But for matrix multiplication, you want the second dimension in y minus y hat to be the same as the first dimension in x. So after we transpose it, x would be 100 by 1. Yeah, so that's what we expect. All right, do we have any more questions? Or are we good to go? All right, I think we're good. Let's just, yeah, this is definitely the most involved part of this workshop, which is implementing the gradient descent. And this would, I guess, test your understanding of gradient descent when we covered it in our workshops. So if you have any questions along the way, feel free to ask us. Because we know that it's been a while, so we don't expect you guys to remember like every single thing that we said, that we covered about linear regression. So if you need any like refreshers, then yeah, feel free to ask us. We'll be happy to take your questions. Okay, so let's set alpha to learning rate. And let's initialize our loss to be just a list of empty lists. All right, so now we're ready to train our model. So we're gonna, I guess, just do like 50 epoch. So we're just gonna, I guess, run through our training data set like 50 times. So, all right, so let's actually divide this function into parts. So the first exercise is to, I guess, store our predictions in an array. So the exercise would be just, I guess, get the predictions using the weights and bias and x that we have initialized using a function that we have defined. So that should be just one line, should be pretty short. Give you guys like 30 seconds to think about it. All right, does anyone want to take a guess what the answer is? Feel free to post it in chat. Predictions equals y hat wbx. Okay, that's exactly what I'm looking for, so well done. Whoops. Oh wait, I didn't even run this. All right, so now that we have our predictions, let's get the gradients. Also using a function that we have defined earlier. So let's see. We need x and y and I guess our predictions in order to compute the gradients. I guess we can just store this in grads. Because why not? All right, I'll give you guys, I guess, a minute to think about it again. If you have the answer, feel free to post it in chat. Okay, grads equals gradients x comma y comma predictions. That's the correct answer. Really can't type today. Feels bad, man. Okay. So now that we have our gradients, we're just gonna store, I guess, access the entries in our dictionary and store them in, I guess, variables. I guess this is not completely necessary, but it is just for like better, readability. All right, so now that we have our gradients with respect to our weight and bias, so it's time to update our model. So I guess, yeah, now it's just updating WB. This should take 2 lines. So I'll give you guys another minute to think about how to update our weights and bias using the equations that we have, or at least I put up here. All right, if you have the answer, feel free to post it in chat. Okay, someone said W equals W minus equals alpha times dW, so that is the right answer, and it's basically the same for our bias, because as you can see, the equation is exactly the same, except the weight is now the bias. So, all right. So now our gradient descent is working. So I guess the last step really is just to compute the loss. And this is, I guess, just for our own information. It's like this step is not necessary for gradient descent to run, but as you'll see, we're gonna do some cool visualization after running our gradient descent. So yeah, we kind of need to, I guess, keep track of what our loss is if we want to like visualize it. And we're just gonna return, I guess, our weight, bias, and loss. And this should be good. All right, is everyone good up to this point? Feel free to shoot me any questions if you have any. I guess now that we have fully defined how linear regression works, now would be time to actually run it. Oh, will grads dW be 2-dimensional? White W is W is 1-dimensional. Okay, I guess your question is saying, like, if we have if W is an array, will dW be 2-dimensional? So I guess that means it's a matrix. So I guess if W is 1-dimensional, the gradients should also be 1-dimensional, because we're just taking the gradients of the partial derivative of W with respect to each weight. So it should have the same dimension as our weight matrix, if that makes sense. But in this case, W is just a scalar, so dW is also a scalar. I hope that answers your question. But yeah, we're gonna do like a more complex example in the next workshop. So we're gonna definitely encounter the case when W is like an array. So it's good that you brought that up. All right, so let's, I guess, wait. Yeah, actually, I'll leave this as an exercise. So run linear regression using the gradient descent function that we just defined. I guess you guys should probably like set the learning rate to something relatively small, like 0.03, because if you start with like a large learning rate, it's definitely possible that your loss would just start diverging, and that's not good. So this should be just one line. Oh, I mean, will grads have shape of 1, 1? Yes, because I think NP dot. So y hat minus y is 1 by 100, right? And x transpose is 100 by 1. So the product of these two matrices would be 1 by 1. So yes, that's a good observation. I guess we want to store the output to WBN losses for the lack of creativity. If any of you guys have the answer, feel free to post it in chat. That'll be greatly appreciated. Are we from W with shape 1, comma? Oh, that's a good point. Yes, so W has shape 1, comma nothing, but I think this should still work. But that's a good observation. I guess we will find out whether that works in just a minute. All right, does anyone take a guess of? Okay, actually, you know what? I think it's kind of self-explanatory, so I guess I'll just do it. Okay. I guess there's a bug somewhere. Well, that's kind of awkward. Operands could not broadcast together with shape 1, 100 and 1 by 3. Wait, does that something? Huh. Oh, I know why, because I redefined B. Okay, that was really dumb. I shouldn't have redefined B. I just have to run this cell again. Hopefully this should work. Oh, actually, yeah, that's a good point, because yeah, so W is 1, comma nothing, so I actually have to reshape W to 1 by 1, and I have to do the same for B. Right, now that we have the right shape, hopefully this should work. All right, it does. Sorry for a hiccup there. Yeah, I didn't realize I redefined B when I was doing the NP dot thing. All right, so I guess now would be a good time to inspect what W and B is. So as you can see, W is pretty close to pi, which is the slope of the function that we're trying to model, and B is kind of close to 10, which is the y-intercept. And I guess, so the gradient descent part is basically done. And now we would just, I guess, visualize it. So let's do some matplotlib stuff with a plt.scatter x comma y comma, I guess we'll just set the alpha to 0.5. And let's do the same for, I guess, y hat. Equals 0.5 again. Guess I'll just call PLT show just for sake of completeness. So, okay, so as you can see, the line that we're modeling, or the line that we're trying to model is the blue line. And we can double check. And I guess the line that we're running linear regression on is the orange line. So like we expect, these two lines are pretty close. And we have a lot of questions. Okay. Can you show us how you reshape W and B? Yes, W equals W dot reshape 1, 1. Okay, yeah, I think that question is answered. So let's also go through what the loss looks like. So you can do this with PLT dot plot, and we can do, I guess, we're gonna just generate some data on the fly with the range function and our losses. So as you can see, our losses are decreasing, which is a good sign. So actually, now that we have our linear regression running, let's explore a little more about the effects of different learning rate. Okay, all right, I guess I can zoom out. All right, so this is the first graph. Wait, or do you mean the graph before training? Yeah, I'm just gonna assume this is the right graph. No, that's good, thanks. Okay, cool. All right, let's add a Markdown Cell, I guess. Effects of different, can't type today. When I try reshape, it says value error, cannot reshape. Okay, yes, because I made the mistake of I guess redefining B to A without realizing that I previously defined B. So basically you have to run this cell again before you could reshape. That was my bad. I shouldn't have used B in the example of np dot dot. Can you show your gradient descent function again? Yes. Let's go through some more questions. Is there a README for this lesson? Okay, so yeah, I'm gonna upload this notebook to our GitHub page, which has like a data set right now, which I guess we're not gonna get to in this workshop, but yes, I'll upload this notebook to the GitHub for workshop 7. It works, lol, thanks. Okay, yeah. It's good that it works. I was actually like, I panicked for a little bit when it didn't work. Why do we use range 50? Okay, I guess this is just a for loop, like how you do for loop in Python. So what range 50 basically generates is, I guess, like an array of values from, actually not an array, that's not accurate. It's basically I would go from 0 to 49 because let me just do a quick demo right now. It's I. Invalid syntax. And do it. Wait, why is it not printing? Okay. Yeah, so we're going from 0 to 49. So it's just like you do how you do like for I int I equals 0, I less than 50, I plus plus in I guess C or Java. For I in range 50 is just a standard way to do for loops in Python. Okay, let's see. Like there's significance of 50. Oh, I guess this is just like an arbitrary number. Like this is just like how many times we're gonna do gradient descent. And I figured it's just like a good point to stop. Yeah, I guess like if you want to play devil's advocate, like if we do 100, if we go through our training data 100 times, hopefully the bias will be closer to 10, because now it's not really close and it's kind of bugging me. So W is pretty close to pi, and our bias is 9.999. So that's a lot closer to 10. And let's graph this again. So yeah, now they're basically just overlapping. And the loss should be, a lot lower. All right. I guess if we're all good, we can go to the learning rate part. All right, let's test out, I guess, a bunch of different learning rates. I guess I'll just I guess this is kind of a wordy name, but I guess just for clarity, I'll do it. Learning rate is 0.01. So we did 0.03, I think, for the first one. So we're just going to do 0.01, which is 3 times smaller. And we're going to do, actually, I should just focus on typing. Large alpha equals gradient x comma y comma. Oh wait, I forgot to pass in. Wait, actually I have to. Okay. Actually, I have to initialize some more variables. W small alpha. I guess I'll just initialize this into 0. Wait. Crap. That's not what I want to do. Bias small alpha. And W large alpha. It's 0.03 or 0.1. So this is about, I guess, 3 times larger than the learning rate that we're currently using. So let's see what's going to happen. Large alpha. Oh, okay, that was really dumb. Oh, okay. Yeah, sorry about the typo there. All right. All right, so now that we have all the weight and bias for and losses for our different alphas, we can plot them or visualize them using some more matplotlib stuff. So let's do matplotlib. Actually, I can just copy and paste, right? And just copy and paste and change some stuff. Okay. So this should be, I guess the range doesn't really matter. We'll just do small alpha here. And we'll label this as, I guess, small learning rate. And this is just a regular, so we'll just label it as, I guess, medium learning rate. And this large alpha, we'll label this as large learning rate. And we'll do PLT legend to show, I guess, to show the labels. Oh wait, did I redefine? Wait, something happened to my weight or the loss. I have to rerun some cells. Something unexpected happened. Okay, the losses here looks good. Okay, that's what okay. All right, so as you can see, the small learning rate, the losses for a small learning rate is decreasing the slowest because we're taking a small step every iteration, and the losses for medium learning rate is in between the small learning rate and the large learning rate, and the losses for a large learning rate is decreasing the fastest. So yeah, that is what the effect of different learning rates on gradient descent. And if you just have like a learning rate that's way too large, your loss is gonna diverge. So I guess I could demonstrate that real quick, what that means. Let's see if 0.5 diverges. Okay. Guess PLT plot. Let's see if this diverges. Yeah, so you can see the losses here diverges. Oh wait, no, actually I did run gradient descent. Okay, there are some questions in chat. Can you please go back to the gradient descent code and graph? Yeah. So do you mean like here or here?
The first part.
Oh, so like the function?
Yeah, like when I run my code, it says non-broadcastable output operand with shape 1, doesn't match the broadcast shape 1, 1, and at the line W minus equal alpha times DW. Okay,
yeah, I think, yes, so as someone pointed out earlier, I guess the gradient for DW is actually 1 by 1. So what you have to do is you have to reshape. You have to first reinitialize what B is, because I accidentally like redefined B here. So you have to reinitialize B. So you should get, okay, actually let's add a new cell. So W, or yeah, W. Oh wait. Okay, so if you run this, and W should have shape 1, 0 or 1, nothing. And then, so what you have to do is you have to reshape W and B. And then now W will have shape one by one. So now that we have reshaped W, we can actually like multiply W by, or we can modify W by its gradient because they have the same dimensions now. Does that answer your question?
Yeah.
And also like don't run these cells again.
So like, mathematically speaking, there's not a difference between 1 comma like nothing and 1 comma 1, right?
I guess technically speaking, like 1 comma nothing is basically a matrix with 1 row and no column. So that would be a 1-dimension vector, I guess. And 1 by 1 is like a matrix with 1 row and 1 column.
Okay.
So I guess you can't multiply a 1-dimensional object with a 2-dimensional, or you can't subtract a 1-dimensional object from a 2-dimensional object. Like, I guess just like syntactically in Python, that's an issue, but
Okay.
so like for formality, we have to reshape W.
Okay, could you please go down to that code like after when we run like cell, yeah, that one. A little bit more down when we have the first graph after. Okay.
Okay.
Yeah. I just want to relook at it. Thank you.
Yeah, so I guess this will all be like, this notebook will be uploaded to GitHub shortly after the workshop. I'll do some, I'll make sure there's no bugs. Sorry about the bugs that I encountered. And I guess is there any more questions? Can you go back to gradients function? Okay. Yeah, so the gradient function is just, we're basically defining an empty dictionary that's going to store the gradients of, or the partial derivatives of the loss function in respect to our weights and bias. And we're just basically storing these in. So we're basically just computing what our gradients are, and then we're just storing into our dictionary. All right.
I'm just getting a weird error where it says tuple object does not support item assignment.
Wait, which cell is that?
It's in the gradient descent cell for me. Oh, sorry, the gradient cell for me.
Okay, I'm assuming it's you ran this cell and then you got an error that points to the gradient cell.
Yeah.
All right, I guess we should end the workshop right now officially because this is what I want to cover. So I guess it'll be easier if you could like, I'm just gonna stop sharing screen. So if you could share screen.